Okay, so this is section 1.3, matter and volume. Our second definition that's going to help us build our model of matter is volume, a term that you're probably familiar with, but one that we have to take a closer look down at the molecular level to actually understand what we mean by volume. So let's first take a look at finding the volumes of solids. A definition we'll use for volume is just the total amount of three-dimensional space taken up by an object. And if we think about that for solids, that particular measurement is done indirectly. What I mean by that is we actually have to measure a few times to get a couple of data points, and then we have to take those points and mathematically rearrange them or put them into an equation to solve for the volume of a solid. So let's look at a simple solid to start out. Try to get a cube here. That looks pretty good. Alright, and if we wanted to solve for the volume of the cube, I'm sure you've done this in math class before. Let's say that this side of the cube is 5 centimeters and the depth of the cube is 2 centimeters. Okay, and the width of the cube down here is 4 centimeters. We know that the equation for this particular cube for the volume is just length times width times height. And in our case, that'd be 5 centimeters times 4 centimeters times 2 centimeters. And if you do the math correctly, you're going to find that that equals 40 centimeters cubed. And this is important right here. In the sciences, just solving for a number is never enough. You're always going to have a unit that is associated with the number that you're working with. And in this case, our unit is right here. It's the centimeters cubed. Okay, so we need to be sure we have a unit attached to all of our numbers. All right, so that's pretty simple. Let's take a look at another solid that may be just a little bit more difficult. Let's say we've got a cylinder. There's a horrible cylinder. But a cylinder nonetheless. All right, there's our cylinder. And we wanted to find the volume of that cylinder. We'll be working with this equation quite a bit here in these first couple of, I got to redraw this, it's just going to bug me, in this first chapter. So that is really no better, but it will have to do. So we want to know what that equation is. Well, the equation for the volume of a cylinder equals pi r squared times the height of the cylinder. So pi times r squared times height. And if you're wondering where that comes from, if you remember the equation for the area of a circle, right, is just pi r squared. Okay, pi r squared. And r, if you remember, is going to be the radius of that circle. So we'd have to tip that cylinder on end, and we'd find its radius right there. Okay. We'd square that, multiply it by pi, and h is actually going to be just the height of our cylinder. So how tall is it? Right? So to find the volume of solids, we've got to measure them with a tool and then do a little bit of math with those measurements to find the volume. So that's why we term it an indirect measurement. Okay, the next type of phase of matter, liquids, these are a little bit easier to find their volumes because we can measure them directly. We can use a lot of different tools to do this. We can use a beaker. We can use a graduated cylinder, which you should be getting familiar with in this first lab. And we can use a volumetric flask, something you probably won't use a lot in this course, but it's very accurate. So we can actually find the volume of a material that's in a flask down to the second decimal place. So we could say 20.00 milliliters, and that's pretty accurate stuff. When we measure a liquid, we have some common units that we use. We saw in the previous example, when we did volumes of solids, centimeters cubed seem to be the pretty common unit. But for units of liquids, we're typically going to use the liter in science. And if we want small volumes of things, we'll use the milliliter. I don't have the abbreviation on there, so this is the milliliter, little m, big L. Okay, the milliliter. And since we're here in the United States, we don't have a good picture of what a liter is. If you lived in any other country, this would be a piece of cake, but you live in the U.S., so you have to really think about what the heck a liter is. Here's an example. This is my my bottle that you probably see me drinking out of during class. That's a liter. All right, there you go. 4 of those, a little bit more than 4 of those, makes up a gallon. Okay, so I got to drink 4 of those a day, which I struggle doing, but I try to drink a gallon of water. There you go. So that's a liter, and that's a common unit used in science for volume. One important thing I want to touch upon that when you're measuring liquids is that you have to understand that when you measure liquids inside of a graduated cylinder, liquids tend to have these principles called cohesion and adhesion. So they stick to each other and they stick to the cylinder they're in. And so you get this little like bevel that swoops up and down here. We call this thing a meniscus, okay, just like the meniscus in your knee. And when you're reading the volume of a liquid, you want to read the bottom of that meniscus, right down there. Okay, you don't want to read the top. You can see there's about a 1 to 2 milliliter difference there with this picture. I guess so if I was reading this particular cylinder, I'd go probably 19.4 milliliters. 19.4 milliliters. All right. The last state of matter, then obviously gases. Gases are really interesting because they fill the container they're in. So if you have a container full of nitrogen gas and you open it up, that nitrogen gas is going to fill the new container, which is the room. It's just going to expand into the room. And its new container is the room. This is weird because if your initial container was, I don't know, a liter, and the room, its total volume is like, well, let's just throw 10,000 liters out there. It's a small room, but 10,000 liters. Then the new volume of your gas is 10,000 liters. So it's like grown. It's gotten huge. It's gotten bigger. And that's just because gas molecules don't stick together to one another. They spread apart very easily. So we always say that the volume of the container equals the volume of the gas. We don't have graduations on a cylinder that we have to read. We just look at the side of the container and, well, okay, that's how much gas is in there. Units for gases, because, let me go back. Units for gases, we also use liters and milliliters a lot, so we can use liters and milliliters, but we can also use centimeters cubed, or cubic centimeters, and you use this one quite a bit. So you use cubic centimeters if you've got like a box or a cylinder or something, and you know the volume of the cylinder in cubic centimeters, that's how much gas you have. By the way, cubic centimeters, you often hear that in the medical field as cc. So if you need like 100 cc's of saline, that's a common IV drip, okay, to get electrolytes back into the system if you're dehydrated. There you go. Okay. So cc's, centimeters cubed. All right, if you ever see this little thing in the upper right-hand corner, this little X or the cross-out circle, it means don't write these down as notes. I just want you to think about these things for tomorrow. Number 1. Now that we know what volume is, we want to ask the question, can the volume of a substance change, even though the mass stays the same? Is that possible? And number 2, is there any relationship between the volume of an object in milliliters and the volume of that same object in centimeters cubed? Right? We'll attack these things in the future.